All right, welcome to the APIs How Hard Can They Be talk. Today we're going to be talking about what it means to write good APIs, why you might want to be careful about managing your API surface, and how you can pull everything together to put together an overall API management strategy. I'm Alan Viverette. I'm on the developer experience team at Google, and this is Aurimas Liutikas. And we've been working on APIs and helping library and platform developers provide a better user experience for quite a while now. So, why do we care about APIs? Well, if you're a library developer, you probably spend a lot of time thinking about your product in terms of your API surface. But this talk is just as relevant to folks working on multi-module projects or trying to manage an internal surface between multiple developers. APIs are how your software interacts with other software written by people, and sometimes that person is a developer on the other side of the world, sometimes it's you from a month ago, sometimes it's a large language model, and in all of these cases, APIs are going to play an important role in how efficiently you can write your software and the overall quality of the software that you're producing. So when different people use your APIs, they're going to have different expectations. And in Jetpack, we've built up a collection of different types of API surfaces with different policies and processes associated with them. So first we have public APIs, and these are the APIs that you're going to see documented on our websites. These are what you're going to see in autocomplete, and these are the most widely used APIs, and are effectively permanent once you release them. So for this reason, public APIs are going to have the most strict policies, and generally they're going to have the highest quality bar. Sometimes we need an escape hatch from making hard choices like that. So we have experimental APIs. These are APIs that may have a longer life cycle than a library itself. So maybe you move to stable, but you still have some APIs that are going to still be under development, could be removed, could be changed. We have to be very careful about encouraging experimental APIs to move to public, because if something is experimental for long enough, actually now it's de facto stable and you have enough people using it that you can never change it. And I mentioned that experimental APIs are still public APIs. So these are documented, these are going to show up in autocomplete, and they will get adoption over time. But we have a third category as well. For internal use, we have restricted APIs. These are things that don't quite match up with language visibility of internal or private, and might be some internal implementation details that we, as people developing a couple of libraries in an area, want to use between just our libraries. So what this looks like in practice is we might have a testing library that accesses internal implementation details of the library that's helping developers test. And that means that we have some constraints because of semantic versioning on the changes that we can make to these APIs. So if room testing was using a function from room common at 1.0, room common decides to remove that API, we can't just have room testing follow normal semantic versioning and say, oh, you can use the next version of room common. So we introduced the concept of atomic groups. So these are libraries that must be used at the same version. The implementation is Gradle module metadata that reciprocally says room testing requires room common 1.0 or greater. Room common requires 1.0 or greater of room testing when they're used together. It's not a direct dependency, it's a constraint. So if you update one, you'll automatically get the other updated. And what this means is we can have more flexibility around changing internal APIs because we're guaranteed that we're going to have that same version. All right, so if good APIs can result in better user experience, what makes an API good? And ideally, can we capture that in a tool and automate it? And the answer is sometimes, because APIs are hard. So the first principle that we're going to talk about is consistency. And for Jetpack, we have around 500 developers that are writing around 500 artifacts that we're releasing now. It's a lot. But we want them to feel like they were written by the same person. Developers should be able to build muscle memory for the different naming patterns and conventions that they're going to see in your library. And they should be able to use multiple libraries, whether they're in the same atomic group or anything that's within Jetpack, without having to be constantly swapping back and forth between documentation and trying to figure out how to make one library work with the concepts of another library. Everything should feel like it fits together. Our second principle is usability. And one of the fun things that I learned when I started working on Jetpack was that at Google, they'll actually bring developers in, sit them behind like one-way glass, and do the same sort of thing that you would expect for a UI user study of give someone a task, watch them use your API, watch them struggle, and then make some fixes. So you can also do this at home, or you can try writing sample code and put yourself in the shoes of someone who's actually using your library. Writing integration tests or writing unit tests can also get you further in this direction. And actually, the room testing library that we mentioned plays a big role. So making sure that developers are able to test the APIs that you write. And a good way to make sure that that's true is trying to write your own integration tests and then write tests for those. So at a minimum, we do recommend following common conventions for a language, so writing idiomatic Kotlin code, and providing enough documentation the developer can understand how to use your APIs, what the contracts are, and if there are any new concepts that you're introducing. All right, and finally, the big one, compatibility. Everyone's probably had the experience of updating libraries and your code breaks, or there's another library that you have to update because there's some incompatibility in some old version, and now your library expects a new one. Or maybe you end up wedged because some library expects one version and another expects a different version, and there's no way to reconcile those. So we really try to avoid that in Jetpack. So we focus on 3 types of compatibility. First is contract compatibility. As I mentioned, it's important to document your APIs and say what the API does. Part of that is embedded in the method signature, but a lot of that is going to be just explaining, this is also really helpful for LLMs, explaining in text what the API does, what behavior you can expect from it, and you need to guarantee that that's going to be true in the future as well. So that's really hard to automate, but if you have a good suite of integration tests, a good suite of unit tests, you can approach something really close to perfect contract compatibility. And in Jetpack, we actually run millions of tests in the Google repository to make sure that we're still following contract compatibility. So what this looks like in practice is, let's say I'm implementing an advanced math library, and I decide I want to make some changes to how addition works. Probably a bad idea. So I shouldn't make a change that doesn't match up with the documentation. Addition shouldn't just return 0, because this is going to break a bunch of code that relies on addition working as documented. And technically, I could go in and change the documentation to say, oh, you know what? Actually, addition always returns 0, so the contract is fine. Unfortunately, this is going to break all of the integration tests that expect addition to work a certain way. And this is why it's important to write a bunch of tests. All right, next up we have source compatibility. What this means is when I update something, does a developer have to change their source code? And this can be tricky to manage because some source incompatible changes, in my personal experience, adding generics in Java to Android's find view by ID, imposed a huge one-time cost on developers because it added ambiguity. It meant people had to update a ton of source code. But we decided that this was actually a really good time to break source compatibility because the overall developer experience, long-term, permanent, became a lot better. So you have to be careful with source compatibility. Sometimes it's okay to break it. And finally, we'll talk about binary compatibility. This is a really difficult one. It means whether your compiled code works with other compiled code. And the rules of binary compatibility are language specific. So Java compatibility spec is really well documented. There are a bunch of great resources. But understanding all of these resources is really, really hard. And Aurimas is going to get into that in just a minute. And this is why we leave it up to tooling whenever possible. This is also, I think, one of the most important aspects of compatibility because this is where you can become completely wedged. When a library that you depend on expects one version of something in your transitive dependencies, maybe your code expects another, and if they break binary compatibility, maybe the 1.0 isn't going to work anymore and you need to pull in the 2.0. So let's go through an example of that. Let's say that I don't want my advanced math library to handle addition anymore. I'm just going to remove the function. So what this means for an application developer is they're going to have to update their source code. This is source breaking. Kind of a pain, but maybe we can find some other way to add 2 numbers. For a library developer, also source breaking, but now I have to do another release of my library. And I'm going to have to pull in whatever major version bump I did for my math library. So my library now depends on 2.0, doesn't have addition anymore. But for an application developer, it depends on my pre-built, and maybe depends on something else that depends on an older version of this math library. I now have 2 versions that I need to use at the same time on the same compile class path. And that's not going to work. So I can't compile until maybe Google goes and updates to a newer version of this library, and that might take a while. All right, so we've learned a little bit about what types of compatibility we have. Now over to Aurimas to show us some fun examples.
Cool. Thanks, Alan. Yeah, so I kind of want to talk about like how could you break? Like a lot of it is theoretical, like some of it is kind of examples, maybe obvious, but I want to kind of give you a little bit of appreciation for the art of API evolution. You know, I really want to kind of show it in a way that you might receive it, which essentially is kind of like a style of a pull request, right? You have a piece of code, someone makes a change, you know, what happens? So let's say we have something very simple. You know, it's a class or a file, a Kotlin file that has a top level function. And someone sends you a PR request that just renames that file, right? It looks very innocent. It looks reasonable. Like what could go wrong? But to kind of really understand what went down is we can really use a tool called JavaP, which is a disassembler. And what it allows you to take is take a class file and convert it to something that is human readable. So it kind of like lets you really digest of what code you produced. So we'll use this tool to kind of walk through the example and understand what went down when we renamed the file. Because JVM has no concept of classless functions, you cannot just have it hovering in the air without it being attached to something. So what Kotlin does, it creates a facade class that allows you to put these top-level functions in a place. And the way it does it, it actually uses the name of the file to name the facade class, right? So if you had example 1, it will just name it example KT, and then that's where your function is going to live. And if someone renames that file, the facade class name changes, right? And now you are essentially making a pretty drastic change because one class disappears and another one appears. And in fact, what happens is for Java users, you break everything. You break source compatibility, you break binary compatibility, and you break contract because it's gone. For Kotlin, it's a little bit better because you still preserve source compatibility because the way Kotlin determines what is the name of that function, it doesn't actually use the name of the facade class, so you're able to find it, but you broke everything else. So at that point, like, is it the change you want to do? Let's take another example. Let's say we have a class and we just added a constructor to it. It's a very simple change. Someone is adding a thing and it takes a string now. Like it looks safe. It seems reasonable. But what actually goes down is that if you look at the original before the change, we already had an implicit constructor in this class, and that's the thing you really have to kind of remember that it happens. That if you don't declare a private constructor to start with, you're going to have a public one out of the box. And when you make the change, you actually strip that constructor out of the way, and now someone who might have called that constructor is going to crash, right? Because you kind of removed the compatibility for them. And here we just break everything. It's just like the worst case scenario. And it's even worse because it doesn't look bad because you look at it and you're like, oh, I just added a constructor. Why would that be wrong? And the fact is that you hidden something and took away something that was not explicit. Another thing that we might have as a PR is someone takes an interface and then adds a method with a default implementation. It looks safe, right? It looks very reasonable. It looks like nothing could go wrong. The problem is if you pick a name that is actually very common. So imagine I added a method that's called close. Many classes probably implement their own close method. And if you happen to match that name and they have had a different implementation, now you're in a world of pain because you probably are not doing the same thing as the user wanted. And you're most likely now also going to break source compatibility because the user is going to have to add an override modifier to their method. So you're kind of like doing something that looks innocent. And in fact, it is binary compatible because you're not breaking the binary compatibility, but you're breaking the source and contract compatibility. One more example I'm going to throw at you is, taking a method and changing the parameter that we take from string to a super type that is char sequence. Again, intuitively, it looks safe because if you try to use this class, it would work. And it is, in fact, source compatible. But let's take a look and see how it actually would go down. Let's see, I have a call site. I call this method. I pass my name in there. It all looks nice. And if we use JavaP, there's also an additional parameter you can pass into is -c, which essentially kind of like allows us to see the complete view of the class, even implementation details of the method. And we can see that the call site actually inlines the parameter type, right? So the fact that it was a string to start with is part of the contract of calling into that method. So if you go and rip out and change the type, you actually broke all of the call sites. So you broke binary compatibility for all of your users. Well, hopefully at this point, your eyes are glazed over. Maybe you're a little bit worried and stressed out that oh my God, I don't want to memorize all of these rules and figure out every way it could break. And we relate to that. We kind of started in that world where we were just kind of winging it. And of course, that's when you make mistakes and you kind of learn, what could go wrong. So let's talk about some real examples that happen in our code base to kind of give you an illustrative thing where even if you try to do your best, you can still mess up, and that will result in a really bad experience for your end users. So in 2023, we had a change that was deleting some stuff that looked like unused, and it was an AndroidX SQLite library after we changed our minimum supported version of Android. Let's not focus too hard on who reviewed and approved this change. It's an innocent-looking change because it's just deleting a bunch of unused code, right? It says, Android API 16, and we're at that point moved to API 21. So this was really not a useful piece of code. It was, should be dead code. All the PR validations passed, changed, merged. It was awesome. We were done. Where are we? 16 months later, we get a bug where someone is reporting a crash in AndroidX Room library where it's failing to find this API 19 impl class in SQLite. And so what went wrong here is we had accidentally marked some of the things that we were actually using cross library groups as internal implementation. And so all of our tooling that is supposed to kind of help us catch these type of bugs was just oh, it's fine to change. Only you could be using this. And that essentially caused the breakage because we were able to change this thing. And this type of stuff is pretty tricky because you have to be really careful in what is using what and where. And the workaround for us was to add all the dead code back, right? In fact, not dead code because it was used, right? If you have a mismatch of the versions, you kind of have to maintain that binary compatibility, which sucks. But we kind of set ourselves up for that, so we had to go and put it back. And how do we prevent these type of regressions, because we don't want to do this again, is we built ourselves an Android lint static analysis check that essentially catches any of these uses across library groups. And that allows us to make sure that if someone tries to start using it, you have to mark it in the right way, and then it will start getting tracked, and we will make sure that we don't break you. So what's the takeaway? You really have to be careful about what you consider your API service. Some of the stuff you write might look like an implementation detail. Some of the stuff is kind of tricky, nitty-gritty things that you really have to pay very close attention. And even if the tool is in place, you might make a mistake. Example number 2, let's take a look at another one. This one is kind of coming from a little bit of the JVM world, but it ended up affecting us. So let's say we have this beautiful method that just takes a list and removes the last item from the thing. It looks very reasonable. It was a method that was added in the JDK 21. So if you're using JDK 21, you're using it, it works, it's great. Kotlin wanted to make this better, so they added a Kotlin extension function to kind of help you use this function on older versions of JDK, so you don't have to wait for JDK 21 to be able to do this thing, which is remove a last item. Very convenient. And the way Kotlin C is implemented is if you have a method that is exact same name and the same parameters as the class, the class method is always prioritized over the extension function. So this essentially allows it, when there is no such method, it will just give you the standard library version. And if you do have it, then it will use the one that's actually on the class path, which kind of works and it looks nicely. And if we kind of use Java P again, we can kind of see if you target Java 17, you get the standard library version. If you target 21, you get the one from the list, which is kind of what you expect, and it's nice. And if you use Android SDK 33 or older, and you just always got the Kotlin standard library version because Android at the time did not have that method in place. So it just kind of worked. Everyone was happy. In API 34, we decided that it would be really nice to add this method so people could just use it without standard library, right? So there's some Java users out there, surprisingly, that still want to do things, and they would also want this method, and so we added it to Android, and the Android platform started shipping it. And if you used the latest device and the latest SDK, it was all happy. It was using the remove last from the list. However, If you were using the latest SDK and you're using an old device, you would crash, because what Kotlin compiler thinks is, oh, on the class path, you have this method on this class, and so I can use it. But on Android, runtime changes, right? So you can have an older device that doesn't have a method. And Android developers are very familiar with it. SDK checks everywhere, right? That's what you know. But this is like very, very subtle, because you won't see that this is happening, or the swap. And your code used to work just fine. You bump the SDK version, and now you're completely crashing at runtime. Is like not a great experience. So there's a workaround. You can tell the Kotlin compiler explicitly, actually, no, I want to use the extension function always. And you can do that by renaming the type, essentially creating an alias for that function. And it will work, right? And what we do now is in Android Lint, we actually catch this for all of the users. And we will tell you to suggest this exact workaround so you don't walk in the same rake that we did. So what's the takeaway here is you really need to be careful about writing extension functions for types you don't own, right? So if you go and write something for a string, for a list, for anything like that, if any of that eventually becomes a real API method for that class, you're just in trouble, right? You're going to have exact same problem that we did here. So hopefully at this point you're like, oh man, I really don't want to learn about any of this. This is so complicated. Hopefully you think that some tooling could help us here. I think we should automate the tedious bits. And what happens to be true is that computers are really good at tedious work. And this is extremely tedious, right? If you're not like a little bit tired and a little bit like frustrated with all the stuff you've seen, hopefully that kind of just gives an example that we should do that. And we have a tool for it. We have a tool called Metalava. What it is an API management tool. It's Apache 2.0, so it's open source and you can use it. It has origins in the Android operating system, because that's where we kind of really started working on the APIs, and then AndroidX and Jetpack was kind of the extension of that, so we continue to use it. And it's a tool owned by Google. What it does, it takes an input of the source of the library, the code you're working on, and it is able to support JVM and Android to kind of reason about what is in the API surface. It allows you to do things like identity comparison. So essentially, it can tell you if the change you made affected the API surface at all. If you made an implementation change and you don't expect anything to happen to your API surface, it will tell you that it's true, that it didn't change. And similarly, it can do compatibility checks, right? So if you're evolving your class and you add a new method, it will let you know, is it safe, is it not safe? And it can do that both for binary compatibility and source compatibility, so we can kind of catch all that type of stuff. And finally, Alan mentioned that consistency is very important. So it also runs API linting, which can essentially suggest things of parameter order, naming of methods, can make sure that you're not passing types that we don't want people to take in an API. Usage of Metalava, pretty simple. It's a Java library. So you just put it on the class path and you call the driver class. And you just pass the sources and the class path of the thing you're working on. And then finally, you declare where you want the API surface to be dumped. And now we'll write out all this stuff. So if we look at an example, the code from a few slides back, we had an example 4 that had a method and it took a string. And it will just kind of essentially dump exactly what you would expect, right? It will take all of the important parts for keeping compatibility for that class and write it out to a file. As I mentioned, it can do compatibility checking. So all you need to do is to swap the last argument, and you say, I want to compare this API surface against this other type. And usually what we do is we pick the last stable version, and that's the comparison for what we want to be compatible against. And when you do that, in the example before where we broke the compatibility, where we took a string and you changed it to a char sequence, Metalava will actually tell you remove the method, right? And now you kind of know, you don't have to think of oh, did I break binary compatibility? Did I not? We have people in the audience like Marcello, who's, has broken stuff, and he probably got lucky that, he didn't have to ship that because, it gets caught in pre-submit before anything lands. And that stuff is awesome. One thing you noted is that we don't support Kotlin native right now. And to do that, we actually adopted a different tool called Binary Compatibility Validator. It's also an API management tool, and it's also Apache 2, but this one is owned by JetBrains. Unlike Metalava, it operates on binary files. So it will take jars, it will take klibs, and so on, and it will let you also do similar manipulation. The big advantage for it is supports Kotlin native, which our tool does not. And we kind of wanted to have coverage as we write more and more our libraries to be Kotlin multi-platform. We want to make sure we don't break our Kotlin native users, because we've built kind of a reputation of good API hygiene and not breaking people, and we want to make sure that we continue that same legacy in native code. So the thing you can get out of the binary compatibility validator is it can give you the identity comparison. So if you make a change that's mostly implementation change, it should tell you like, oh, you changed nothing, good job. But it can only do that for binary because it doesn't read your source. So if you make a source incompatible change, it actually doesn't know about it, so it won't tell you about it. The usage of it is pretty simple. You apply the plugin, and when you saw in the keynote today, they're going to simplify it. You're not going to even have to put a version in there, which is going to be nice. And the way you use it is you just run 2 tasks. One is API dump, which will take the classes you have and then dump it into a signature file, which is very similar to the one we have in Metalava. And then there's an API check, which essentially will run, and it will just give you a diff of the things that have changed if they did change. The downside of this, it's similar to Metalava again as the output, but like it will not tell you if this change is safe or not. You just have to determine it yourself. You squint at it and you're like, this one looks good, and you commit, right? Or you say, oh, now actually no, that changing super types is a bad idea, and then you catch it. So it's a slightly more rudimentary tool in the sense of comparison of the compatibility. Because it was missing some features, we kind of wrote ourselves like a little plus, binary compatibility plus. And what it does, we actually added some compatibility checking into the binary compatibility validator because we wanted the same comfort and people who are converting their libraries from JVM, where they have this really nice experience and catching all these mistakes. We want them to have all the same benefits when we're writing Kotlin native code. And one thing to note is that the rules for Kotlin native are actually different from JVM in some cases. So for example, in Java, it's totally safe to change nullability in terms of binary compatibility, but it is not safe in Kotlin native. If you changed a nullability, you actually broke WASM in JavaScript and Kotlin native. All of those binaries are no longer binary compatible. So it's not great. The rules are also evolving. Kotlin has not finalized the binary spec of Kotlin native. So we're just kind of winging it and making it up, but we're trying our best to make sure that we catch at least the things that we know we can. And we have not published any of the stuff that we have, but we are in open source. If you want to find it, you can. We do plan to upstream parts of it to make sure that community can benefit from the same things that we do. So here, I will hand it over back to Alan and kind of tell you a little bit of how we add APIs to Jetpack.
Thanks, Aurimas. So let's talk a little bit about how all of these tools and recommendations can fit together as an overall API development and release workflow. So in Jetpack, the way that we tend to manage things is we start out with a design doc. This is something that you're going to maybe do a little bit of API fan fiction where you write the API that you want to be using as a user. You're going to focus on what am I trying to accomplish? What are some of the high-level concepts that I'm introducing? And somebody who's experienced, a trained API reviewer is going to take a look at your design doc, and you'll have a little bit of a back and forth to resolve on what you want your API surface to look like. And sometimes this includes just writing out verbatim your entire, all of the method signatures that you're going to be adding in your API surface. Next, you'll start implementing your changes. While you're doing that, you might be doing multiple commits. You're running Metalava to dump your API surface to a text file. You're using that also to run lint as you're writing your APIs to make sure that you follow all of the documented and automated best practices. And then when you finally upload, we have a rel note stanza where if you've made any changes to one of the API files that you've dumped out that you upload, you'll also need to write a little sentence that explains what APIs you added. And we'll talk about release notes again at the end of the release cycle. All right, next up is code review. We happen to use Gerrit as our code review tool. It has a concept of review bits. So normally when you're getting your code reviewed, you'll be asking someone for a code review plus 2 bit, which basically means I approve this change. The implementation looks good. We've added the concept of an API plus 2 bit, where an experienced API reviewer is going to take a look at your code. This might be the same person that reviewed your design doc, in which case it can be a pretty quick review. But they're doing anything that we couldn't automate. So getting an overall sense of, if I was a user of this API, does all of this make sense and fit together? We also run validation in our continuous integration. So in pre-submit, Metalava is running. If you've had previous releases, it's validating the rules that we apply to what can change between minor or major versions or whatever happens to be going on in your CL. So once you've gotten feedback from your reviewer, you've resolved all your feedback, you're able to merge your commit, and we'll move on to things that happen in post-merge. So again, we rely really heavily on continuous integration. So in post-submit, we're running unit tests, we're running integration tests, we're validating contract compatibility, we're running Metalava again to make sure that everything that happened during code review was still reflected in the code that got merged. So we're checking source and binary compatibility. We're also running unit tests and integration tests for people who depend on your library at tip of tree. So that's another way that we enforce contracts and source and binary compatibility. We also have an additional review process to sort of do spot checks on what an individual API reviewer did. So we have groups of like 5 to 6 trained API reviewers that look at every API that lands in Jetpack and also in the Android platform to get a sense of, for someone who's less familiar, may not have been involved in the design doc initially, does this still make sense as an API? Can I read your documentation and generally understand how I would use these? Again, there's sort of a back and forth if people have feedback. Once that's all resolved, you can move to schedule your release. So our release tool is able to look at have all of the changes that you have submitted been reviewed, has all of the feedback to those reviews been resolved, and when you get to that point, you're able to schedule your release. So that's our final validation step, and then we aggregate all of the rel note stanzas between the last Git SHA that was released and the SHA that we're about to release. Library owners review those, and then everything goes out. We generate documentation, we ship things to Google Maven. One other thing to note is by the time we get to post-merge, developers have already moved on and started writing their next set of APIs. So this is an ongoing cycle, and developers are always going to be writing new APIs, and this process of post-merge review happens asynchronously from that. Right, so since 2018, we've learned a lot about how to manage API development at scale. And a lot of what we've talked about today was learned through trial and error and a lot of retrospectives. So I wanted to share a couple of notable lessons that we've learned along the way. First, if it sounded like we do a lot of hands-on review and spend a lot of company time looking at APIs, we do. And it is sometimes a problem. So as Aurimas mentioned, anything that's tedious that we can automate, we should be automating. That means when we identify something that comes up often in code reviews, if that's something that's consistent, and we can, with a very high reliability, automate that with a linter or some sort of static analysis, we should absolutely be spending the time to embed that in a tool so that we never have to talk about it in code review ever again. And providing clear guidelines can be really useful. But you have to make sure that these are high accuracy. If you can't hit like 95, 100% accuracy, make something error level 100% of the time if this shows up, it has to be fixed, you probably shouldn't turn it on because people will learn to ignore warnings. All right, second, as I think we've impressed upon you, writing APIs can be really complicated and scary. And if things are public for long enough, even if they're alpha, even if they're experimental, they're going to become stable. And often it's difficult to get developers to commit to something being stable. So you may have seen libraries that stay in alpha for 17, 18 versions, maybe take 2 years to move from alpha to beta. And that's kind of hedging on, oh, well, we don't know if these APIs are perfect. Users haven't complained too much, but we don't want to commit. Sometimes you have to force people to commit. So we've put timelines on how long APIs can stay experimental. We have cadences that we enforce to make sure that libraries are actually moving along to stable. And we really discourage people from making internal restricted APIs as a crutch for making real, public, well-defined, well-documented APIs. So having a strong system of early design review can help people feel more confident. Having a strong set of documented best practices can really help with that as well. But ultimately, sometimes you just need strict policies to give people a push. All right, and finally, I mentioned that we've been doing this for a long time. We have, in fact, been doing this since before Kotlin was a consideration. So if you look at some of the APIs that we wrote that will be around forever, they might not look good from Kotlin. And our best practices have changed over time. So things like suspend functions, things like moving from builders to having a bunch of default arguments in a constructor. A lot of our best practices have changed specifically for Kotlin. And just generally to better accommodate what developers want. Sometimes you're going to have to choose between consistency with the old APIs that you wrote and following best practices. And we'll tend to prefer consistency. If we have one class, we want to make sure one class that a developer is going to be using used to be written in Java. We converted it to Kotlin. The API surface didn't change. If we add something new, we're probably still going to lean towards that Java format of APIs because we want developers to have muscle memory within that class or within that library. When we're creating absolutely new libraries, some of our new libraries like Compose are focused only on Kotlin users. So we can really fine-tune those APIs to work great from Kotlin. And in a lot of cases, it's going to be a judgment call of, does consistency make more sense here? Or does following language best practices and all of the absolute new things that we think developers want is going to be better?
Cool. So to wrap it up a little bit, I wanted to kind of like answer the question that we posed in the very beginning, right? Like should you be doing, like why should you be tracking your APIs? And hopefully some of it has been like, oh my God, I really don't want to learn about this, and this is one of convictions. But like let's talk about it, right? So machines are great at tedious tasks. They're that's their job. Like that's how they're created. And humans are really bad at tedious tasks, right? If you squint at something, you're most likely going to miss a thing that you actually care about. So offloading the work you probably don't want to do to a thing that is really good at it is often a good idea. So this is one of those cases where I think it's much better than having to go and study Eclipse Java manual of how to evolve binary compatibility. Instead of doing that, you write a tool that knows how to do that for you, right? That's a good thing. Another thing of like when your API changes, you can actually build a process around it. So one useful example is you go from your library 1.0 to 1.2 or 1.1, and then now you can actually tell what's changed in your library, right? You can squint at it yourself and be like, oh, this is the stuff I've added, right? And you can tell your users, this is what's changed. If you don't have API tracking, it's really difficult for you to know what's even changed. And it also can give you a signal of like, okay, like this has been experimental for a very long time. Should it move to stable? And if you have the tracking, you can actually tell when it is instead of going and doing like some Git diving to make sure the history reflects what you want. And all of that taken away, right? Like if you're not spending your time figuring out, are you going to break binary compatibility? Are you going to break source compatibility? Are you doing something that's going to break someone somewhere? You can actually focus on a good API design, right? If you're not thinking about the stuff that's tedious, you're focusing on like, is this a good use case? Should I be using flows here? Should I be using suspend functions? Should I shape this in a different way? Should I write a wrapper, right? If you have time left right now, you can do these things that are really, really handy. Cool. So with that, I want to thank you for attending. We'll have a couple of minutes for questions. If you have anything, you can feel free to ask. We have links to the things that we talked about if you want to take a look. And then don't forget to vote. Thank you.